Good day, everybody. A key term here you might not be familiar with is this notion of self-inverting. And what this really means is the number is its own reciprocal in modular arithmetic. And so we're looking for the sum of all self-inverting integers modulo 7 between 1 and 50. And we're supposed to find the least residue of this sum mod 13. So we're switching moduli. It's really not much of a problem. It's just checking to see if you understand the definitions. But again, what we mean by self-inverting here is exactly what you might expect. A number is its own reciprocal. If you multiply a number by itself, you get 1. And there's no real numbers that way other than 1, I guess. But you can get as many as you want in modular arithmetic. All right. So it's easy to verify that only 1 and 6. And by least residue, I just mean the integers between 0 and 6 inclusive. Okay, those are the possible remainders when you divide by 7. Okay, and just to see what we're talking about here, 6 squared, right, is equal to 36, but that's certainly congruent to 1 mod 7. Okay, and it's certainly clear that's true for 1 as well. And you can check real quickly that none of these, you can prove it theoretically, or you can just check 1, 2, 3, 4, and 5 and see it doesn't work out. Okay, so anyway, 1 and 6 are the only least residue solutions. But remember, we're going up to 50, and we exploit the fact that the simple fact is that 7 is congruent to 0, right? 7 is congruent to 0, obviously, mod 7. And so that's why we can add a multiple of 7k. And in modular arithmetic, this still is just 0, right? But we get these other integers that are outside of the least residue systems, okay? You're just adding multiples of 7 all the way down, all right? And we're using 1 and 6 were the two that we found just in the least residue system, okay? So now, y'all, if it turns out if you add all these numbers up, what this you can see how these add up, and that's something to be proven too, but these add up to multiples of 7 if you look at this. Okay, 35. Okay, and I won't write the rest of them out now, but if you do that and also include the 50, okay, this plus 50, see 50 is not part of this pairing up of multiples of 7. And I won't write it completely out. But what we did is we, just as a slight computational aid, 35's right here, right? 49 would be the next one, right? 49, and so on. The last one would be 91, right? But this ends up adding up to 393. Okay, 393. And you guys can verify I double checked, I'm pretty sure it's right. All right, now what we're supposed to do, we're supposed to reduce this sum modulo 13. Modulo 13, so notice that 393 is equal to 30 times 13 plus 3, right? 30 times 13 is 390. Which of course is congruent to 3 mod 13. So yeah, this is our answer, 3. So I like the problem a little bit. There's nothing deep at all about it. You just have to know what self-inverting means and then do very basic stuff. But self-inverting is not a common type of problem that I've seen in the number theory, the old number theory textbooks. They may call it something else other than self-inverting. I think there's another word for it. But in any event, that is the solution I got. And I plan on doing more of these problems that involve these self-inverting elements. Not that they're hard, but they give rise to classes of new, like for example, you could say something like this. Let's say A and B are self-inverting elements. Okay, say, just for example, A plus B, or A and B are self-inverting elements. If you cube this, you can actually get that this is congruent to 4 times A plus B. You can do some interesting algebra on these things. All right. And if you can almost see this in your head because this is, of course, modulo whatever. Or no, this would be modulo anything, I guess. Yeah, modulo anything. Modulo any prime, probably. But in any event, you can almost see that. If you look at this, when you expand it out, you get a cubed. But you see, a cubed would just become a since a squared is congruent to 1, right? B cubed would become b. And you can see the rest of this. So there's some interesting algebra that you can do on this kind of stuff that leads to some reductions that might help in competition type problems. I haven't seen much of this self-inverting stuff on Olympiad or competition level problems. But anyway, the answer is 3. And thanks for reviewing.